morning. Day 20th. Give me 1 second to take my attendance here. Clark, Price, Day, Sure, Ford, McCarthy, Stewart, David, Norris, Monax, Patel. All righty. So it looks to me like, let me know if I call your name and you're here, let me know. Landon, Ash, I don't see you. Nick, Drew, Evan, Eros, Brady, Sohaib, and Landon Yaki. Are any of you who I just called here? All right. Well, good morning. Hope you're enjoying at least some extra time to sleep in. Let me just show you real quick what we're going to do today. So I'm going to share my screen here. So my plan this go around is we're going to start every day on Zoom at the very least, even if we're not on Zoom the whole time. That way it's clear what you have to do. So I'm going to plan to just at the beginning of class every day, just log into Zoom. It'll be the same link. So we're going to do some notes today. Then what I'm going to do instead of giving you a syllabus this go around is I'm going to give you a few problems to do every day, and there'll be some time for you to work on them at the end. So you'll have some time at the end to work on a daily assignment, and basically, I'm taking the key things from the syllabus, and instead of giving you a syllabus that you have to balance along with all the other things that are changing, I'll just give you a few to work on each day. I'll also point out to you there's some stuff that I don't have time to go over in this format. If you really like algebraic derivations and you really like geometry, you might be interested in watching the episode 1 of bonus physics content that I have recorded. So we would have learned this in class, but it's not really essential. So I'm not gonna require you to watch it, but if you want, that's some information for you there. And then the other thing is after today, chapter 4 test is open to do corrections on the computer portion. So you are welcome to do that after today. So we are going to start by taking some notes. So go ahead and get out something that you can take notes with. Hopefully you have your notebook with you, but if not, just a sheet of paper. And this unit we're going to call uniform circular motion. When you think about uniform circular motion, right, there are several examples of where it's helpful to understand this. So maybe the most obvious example, which we're going to get to by the end of the period, is the orbits of planets, right? Or the orbits of satellites, the orbits of the moon, things like that. So they are approximately circular motion around some object, right? So by the end of this, you'll be able to we'll be able to deal with those. But also, before we get to that, we're going to be able to talk about several other things, like, give me 1 second to, which Landon just came in? Landon, which Landon are you?
Yaki.
All right, thank you. All right, so anyway, the other things, there are some more terrestrial applications of circular motion too, because if you think about like even turning in your car, right? If you turn left in your car, all that is it's just a quarter of a circle, right? So if you understand circular motion, there are a lot of things that you can talk about. So that's kind of what we're going with here. Now I had this all set up. We were going to be doing a lab today to begin this, and it's one of the more fun labs we do. So I'm sorry that we can't do it, but I'll show you at least what we were going to do. So I have these flying pigs here. So I just have this pig tied to the ceiling, and I'm going to turn it on here. And you get, this is an example of uniform circular motion, right? And so I want to use this to talk about what are the key things that you have to have in order to have circular motion. So you're going to notice what's happening here, right, is the thing that is preventing the pig from just going in a straight line is the fact that it's attached to something. And so we're going to talk about circular motion as a combination of two things. You have to have something that makes the pig continue forward, and in our case, that's the wings kind of push it forward. Wait, how do we prove that pigs fly to the world? Well, it's not flying; it's just hanging there. But anyway, so the idea is we need to have some forward motion, but we also have to have something that keeps it going in a circle. And it's the combination of these two things, this forward motion and this force that's going towards that's making it go in a circle, that gives us circular motion. Drew just got here. All right, so let me switch back to my notes camera. So we're going to say uniform circular motion. There are two ingredients for circular motion. The first ingredient is you need some sort of forward velocity. And the second ingredient is you need a force directed toward a fixed center. And we're gonna, there's a vocabulary word for this. We're gonna call a force directed towards a fixed center, we're gonna refer to it as a centripetal force. So I kind of want to kind of draw what's happening here. So I have a, but this could be any object on the end of a string or something, or any object that has some sort of this centripetal force. And what I'm going to do is I'm going to draw this object in 3 different points along the circle. We're going to draw the two things. You have your forward velocity in each case, and that's a vector. And you're going to notice it's a vector that is constantly changing directions. I have a demo I'm about to show you that I misplaced. So give me 1 second here to find where I put that. Well, I'll make another one real quick. Sorry, give me just 1 second here. So we have this this forward motion, this velocity that's constantly changing, and then the other thing that I want to draw is I want to draw the centripetal force. And centripetal force should always point towards the center, and I'm going to call it FC for force centripetal. And you'll notice something interesting here, right? Sorry, you can't see that. You'll notice something interesting here. You'll notice that the centripetal force is always going to be perpendicular to the velocity. And this is a consequence of that fact that you may remember from geometry, where the tangent of a circle is always going to be perpendicular to its radius. So because of that, we can say that these two forces are always perpendicular to each other. So that's interesting, because now we can say there are three things that forces cause accelerations, right? And we know that there are three things that accelerations can do. Accelerations can speed things up, they can slow things down, and they can change their direction. So we've kind of talked about, if you have an acceleration that goes in the same direction as your velocity, you speed up. If you have an acceleration that goes in the opposite direction of your velocity, you slow down. Now we have, if you've got a force that's perpendicular to the velocity, it changes your direction. And if you're constantly changing your direction, the simplest case of that is circular motion. Now, I think of circular motion as a fight between these two ingredients, between forward velocity and a force directed towards a fixed center. And so to give you an example of why I mean that it's a fight between these two, I want to show you a video. So you've probably seen at museums these penny funnels, right? And so the idea is we kind of have approximately circular motion here with these pennies. And what's happening here is you have to have some force again towards the center. So for the pig, we had the string, which was tension, pulling it towards the center. In this case, what we've got is we've got the normal, we've got the funnel, and the normal force on the funnel is always pointing towards the center. And so because of that, that's what's providing our centripetal force. But you have to have both centripetal force and forward velocity. So if you looked a minute ago, there's a moment where these two pennies run into each other. So right there, you saw the two pennies run into each other. So what happened there, right, is when the two pennies hit each other, they lose all their forward velocity. And if your forward velocity leaves, what are you left with? All you're left with is the centripetal force. So if I go back now to my notes here, I have to have both of these things to go in a circle. If all of a sudden I lose all of my forward velocity, what's left? Just centripetal force. I go to the center. That's what happened when those two pennies hit each other, right? So the other example that I want to give, and just a second, I'm going to check off that Evans here before I go on. All right. So the other thing that we can talk about is what happens if all of a sudden you lose your centripetal force. So what I'm going to do here is I'm going to take this, I'll switch here so that you can see me better. I'm going to take this roll of tape and I'm just going to tie a string to it. All right, so I got this. I've got thing of tape on the end of a string, right? And if I make this go in a circle, so again, I have to have my forward velocity and I have to have my string there because the string is what's providing my centripetal force. If all of a sudden I don't have a centripetal force, where does it go? It's just going to go in a straight line. So you have to have both of these things. If you lose this one, sorry, wait for it to come up. If you lose velocity, you're just going to go to the center. If you lose your centripetal force, you're just going to go in a straight line. So you have to have both of these things canceling each other out and exactly balanced in order to have circular motion. Now, there's a way that you can calculate how much centripetal force you need. And sometimes centripetal force comes from more than one source. So we're actually going to refer to it as a net centripetal force. The net centripetal force is going to be equal to the mass times what's called the centripetal acceleration. Right? This is just Newton's second law. I've just tacked some C's onto it. And that centripetal acceleration is going to be equal to v squared over r. So these are the most important equations that you need. Now, like I said, if you would like a derivation of where this came from, there's that bonus video you can watch, but it's not really essential, so I'm not going to derive it for you now. But if you want to, you can watch a video that tells where this came from. And so this is how you would calculate how much centripetal force you need to keep an object going in a circle. There's one other equation I'm going to give you, and that's velocity. The velocity of an object around a circle is equal to 2 pi r over t. So r is going to be the radius. Yeah, radius, that's right. So r is going to be the radius of the circle. And if you look, this equation should actually make sense because velocity is distance divided by time. And the distance around a circle is equal to its circumference, 2 pi r. And this is, you'll notice I put a capital T in the denominator here. Capital T stands for the period. And when I talk about the period of rotation, the period is just the time for one rotation. All right. Any questions so far? All right, I want to say one more thing, and then we're gonna. I'm gonna give you a chance to do some practice here. So give me one moment here. You may have seen this demonstration like this before. It's more fun when you're in person, but we're just gonna make do. So what I've got here, and you're just gonna have to take on faith that it's true. But I've put water at the bottom of this bucket here, right? There's not very much. I don't know if you can see it. There is water in the bottom of this bucket. And we're going to see if we can make the bucket go in a circle without losing any of the water. And I'm going to talk about this here. So if I take this bucket and make sure I don't hit anything and go around my head like this, right? The water doesn't leave the bucket, right? If you don't believe that this happens, right, you've probably experienced something like this. Maybe if you've ridden on a roller coaster, right? Because when you go around the loop in a roller coaster, what do you feel like? You kind of feel like you're pushed down in your seat. That's essentially the same thing that's happening here. However, I want to talk about this because if we look at what we said, if I asked you which force is pushing the water into the bottom of the bucket, what do you think that force is? Feel free to open up your mic or just put it in the chat. What force is it that is keeping the water in the bucket when I swing it over my head like that?
Centrifugal force.
So I see an, and somebody just said something. I heard someone just say something, but I didn't catch it.
Oh, that was me, Shrey.
Shrey, did you say centripetal?
Yeah.
Yeah, so you would think that it might be the centripetal force. The problem is, where does the centripetal force point? It points in, So if you imagine if this was a picture of a bucket, right? What would the centripetal force be doing? It'd be pulling water out of the bucket. So Jack in the chat and Russell as well say inertia. And Aiden, yes. Give me 1 second. You're a little bit ahead of me, but Aiden, you're seeing where we're going with this. But the idea is actually it's the inertia that is what keeps the water in the bucket. It can't be the centripetal because centripetal would pull the water out of the bucket. But think about what this water is doing, right? The water has velocity going this way. And it has velocity and it has inertia, which says if it has this velocity, it wants to keep going this way in a straight line. But what happens? Well, what happens is that a moment later, the bucket's not here anymore, right? So now the bucket's here and it blocked the water from going that way, right? And now the water is trying to go this way. But what happens a moment later? Well, now a moment later, the bucket's here and it blocks the water from going that way. So what happens is the inertia of the water in the bucket makes it want to go in a straight line, but the fact that it's moving in a circle doesn't let it do that. Now, Aiden brings up this idea of equal and opposite forces. Does the water still stay in if you go a lot slower? Landon, that's a good question. You have to have some sort of minimum speed, right? So if I did it slow enough, it would not stay in. Because the idea is you've got to stay in front of which direction the water goes. And to kind of connect this to what Aiden said, right? The reason why you feel heavier when you're going in a rope or when you're going around a loop, or in this case, the reason why the water is pushed down is quote unquote pushed down. It's not because of any force doing it. It's because of the inertia. What you feel or what the water feels is the reaction to that, right? So when you're on a roller coaster and you're going around a loop and you feel like you're being pushed down, you're not really being pushed down. You're actually being pulled in, right? And that force that's pulling you in, that centripetal force that's pulling you in, right, is you're used to that being a reaction to gravity. But it's not. But in this case, your body is used to that being the reaction to gravity. And so it makes you feel like you're heavier. Right. Just to land into your point real quick about how you know you've got to be slower. If you look at this equation, right, you've got to have centripetal acceleration. If that velocity is too small, right, you're not going to get enough acceleration in order to keep it in the bucket. What would be the string on the roller coaster? Good question, Jack. So on a roller coaster, what's happening is it's not the string that's pulling you in, it's the normal force from your chair that's pushing you in, right? So there's kind of two ways to get it. We're talking about a pulling force with a string. In a roller coaster, you've got a pushing force coming from the outside. I don't have it ready right now, but I have another demo that I'll show you on Tuesday that kind of shows how a pushing force can also give you a centripetal force. All right. Any other questions about this right now? Is the length of the string a factor we need to worry about? Well, so this is similar to Landon's question, right? So you have to have the acceleration, which does depend on velocity and R. So you do need to have a fast enough velocity to correspond to whatever your radius is. So the length of the string would be what your radius is. So yes, it does. If we're doing a calculation, it does matter how long the string is. Yeah. Cool. All right, any other questions at this point? All right, here's what I'd like you to do. Like I said, instead of giving you homework on a syllabus, I'm going to give you classwork that you're going to finish before this period's over, so that there is no homework. What I'd like you to do is I'd like you to go in today's folder. There's this document called Day 36 Assignment, right? So basically, instead of doing a syllabus, I've given you 3 problems from the syllabus, and they're right here. What I'd like you to do is I'd like you to do those 3 right now on a separate sheet of paper and then turn it in pardon me, as usual. I have the answers for you to check yourself. But what I thought I'd do is I would stay on here. And then as you have questions while you're doing it, you can ask me the questions. And then once you turn it in, I'll pull it up real quick. I'll check it, and then you're free to go after that. Does that make sense? So let me stop the recording here.